Hey everyone, welcome to Chapter 3, where we start to look at systems of equations, and today we're looking at 3.1, solving systems using tables and graphs. You will need a calculator, so if you do not have a calculator handy, you should pause the video right now and get that ready to go. Our goal today is to solve a linear system using a graph or a table, and we're also going to be using our calculator and a function called intersect to also solve these systems of equations. So what is a system of equations? A system of equations is two or more equations that are working together. So it could be like the cost of two different businesses that you're shopping, or something along those lines. A linear system is two or more linear equations working together. And the solution of the system is the xy value that makes both equations true. So whenever we find a solution, we will write our solution as an ordered pair, x and y. In our first problem here, we're going to solve this two ways, well actually three ways. We'll solve it by graphing, we'll also solve it by using a table, and then thirdly, I'll show you in your calculator how to use the calculator function to solve this linear system. First thing we'll do is we'll write each of these in slope-intercept form. So for the top equation, I had to do a little manipulating. We could add the y over to the right side and then add the 1 back to the left side, and then I just rewrote it in y equals mx plus b. That is in standard form. You could look at finding the intercepts, but the intercepts would be pretty small, so it'd be a little tough to graph that one. So we'll just put it into slope-intercept form. And then the blue equation is already in slope-intercept form. I just flipped it around, so it's y equals mx plus b. We'll start by graphing the red line at a y-intercept of 1 and a slope of 2. Then we can graph the blue line, which has a y-intercept of -2, and then it runs at a slope of 1/2. And where they intersect, ta-da, there's your solution. So we'd be at a solution of an x-coordinate of -2, y-coordinate of -3. So that is the first way that we can solve a system, is by graphing and finding the intersection. Now we'll move on to the second way, which is using a table, and we'll need our calculator for this. In your calculator, you'll head into the y equals, clear out any old equations that you have, and then you can type in both of those equations in slope-intercept form. A little hint: to make a fraction, you can hit alpha, y equals, and then hit that first ND, numerator denominator, opens up a fraction. Once you have your fraction, you'll arrow over to get out of the fraction. Now we can finish our problem, 1/2 x minus 2. And I'm just keeping my color coding the same, so I did blue, and now I'm going to do my red line, 2x plus 1. After you're done putting in each equation, we are going to hit second table. That will open up a table of values. Your solutions for your blue equation are in the blue. Those are your y outputs. Your solution for the red are in the y2 column over here. And to find the solution, we are going to look for when are the y coordinates the same. So I'm looking here, -7/2, -5. Nope, y coordinates aren't the same. I go to the next row, I've got -3, -3. So there's the second way we can find our solution. Both of the equations equal -3 when x is -2, and that shows us our solution. The last way we can find a solution is by finding the point of intersection on your graph. So you can hit the graph button to see a picture. If your graph is not showing up, you're going to want to get used to this key sequence. This is to get back to a normal 10 by 10 window. You're going to hit zoom, then number 6 for zoom standard. That'll bring you back to a 10 by 10 window, and then we can see that basic window and see our graphs being produced. So we want to find out, what is that point of intersection? Now we already know it, it's -2, -3, but it's kind of hard to tell. These graphs aren't very high definition. So we want to figure out, what is this point right here? To do that, we can use a calculator, or a calculate function on our graph by hitting second and then trace, which is this calculate. And then we're going to go down to number 5, intersect, and then you hit enter, enter, enter 3 times, and it'll find your intersection. So the intersection at this point is -2, -3, just like we found using our other two methods. So this method will be really handy when we have graphs that are difficult or equations that are difficult to graph, and then also we can't tell exactly where they're crossing using those graphs with our naked eye. Problem 2, we'll be using our calculator again, so we will practice that intersect problem again. So problem 2 says you want to buy a camera. A film camera costs $89.98 and each photo costs 24 cents. A digital camera costs a little more, $124.48, but each photo costs less, only 9 cents per photo. After how many photos will the overall cost be the same? So here's where you're kind of comparing, you're shopping for two different items. When will the cost of those items be the same? Then you can make decisions based on when those costs are the same. We'll start with the equation for the film camera. So the film camera itself costs $89.98, so that's a one-time fee. Then each photo is going to cost 24 cents. So whenever we see that word like each or every or per, that's going to mean we're going to use multiplication. So we're going to represent our number of photos as X, and then our cost of each photo is 24 cents. Now our digital camera is a little bit more expensive, so we'll have a y-intercept that's a little higher, $124.48. But the slope, 0.09x, is a little bit less. So as the 24 cent slope and the 9 cents, eventually the 24 cents is going to catch up and they will be equal at some point. Now we'll head back to our y equals on our calculator and we will put in each equation. And again, I just matched up the blue and the red like I did in the previous problem. So there are two ways to solve this one. So we'll review using a table. So you can hit second table. Then you can start scrolling and looking for when will the two prices be the same. And I've been scrolling for a while. I'm not getting close yet. The digital is still about $20 more than the film. So here's the next thing we could do. You can hit second table set and the table start. We're going to jump all the way to like 200 pictures. Then you can just hit second table again. Now we can see that the film camera is catching up to the digital camera and we get to 230, and at 230 we have an equal amount for both the film and the digital. So there you have it, using a table, one way to solve this equation. Second way we're going to solve it is using a graph. Now maybe you've already hit graph and you notice and you look and you're not seeing anything. Well, it doesn't mean you did anything wrong. You've got your equations in there. It's just that our window isn't big enough to show the solutions. Thinking about each equation, we have one equation that's got a y-intercept about 90 and another equation that's got a y-intercept of about 125. So we are going to need to make our window a little bigger so that we can see the equations. To adjust your window, you're going to hit the window button. The window right now goes from an x min of -10 to an x max of 10. In some situations like this, we're never going to use negative numbers, so we can make our x min 0. Now I already know the solution is going to be 230 for my x, but maybe I didn't know that, so maybe I'm just going to estimate and I'll put maybe 400 pictures. So I'm going to go on my x-axis, I'm going from 0 to 400. And then for my scale right now I'm counting by ones. Maybe I want to count by 40s. So I have 10 intervals between 0 and 400. For the y as well, we're never going to have a cost that's below 0, so we'll have a 0 as our min. And again, I don't know when the costs will be the same. We're implying that we haven't found the solution yet, so maybe I'll make a y max of 400, and I'll again count by 40. So I just want to make sure my window is big enough so I can start to see those equations, and then I can adjust as I go. So take a second and match your window with mine, and then we'll take a look at the graph. So you'll see your window now just goes into the first quadrant. We've got our film camera, and then we've got our digital camera. And you can see the film camera slope is a little steeper, so eventually it's going to cost more. Our digital camera costs more to start, but it's going to have a lower slope, which causes it eventually to be cheaper, depending on the number of pictures. We're now at the point where we can calculate the intersection because we can see it. So we can't calculate an intersection unless we can see it on our screen. So we're going to hit second, calc, go down to number 5, or you can just hit the number 5, and you just hit enter, 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 and there's our intersection, 230, 145. So there's our second way that we can find the solution to our problem. In problem 3, we're given some data about 2 high schools enrollments, and we are going to check to see if the trends continue. When can the schools expect to have the same enrollment? So as we look at this at a glance, we've got school A, the enrollment is starting to decrease. It goes from 628 down to 612. School B, the enrollment is starting to increase. So we're going to look for the line of best fit for each of these schools, and then we are going to calculate when would they expect to have the same enrollment. So again, we will use our calculator for this. Now we're going to start entering data like we did back in chapter 2. So this will be the first time where we're going to enter 3 columns of data. So we'll start with the years. So like we talked about in chapter 2, we are going to count year 2005 as year 0, and then each year after, we're going to calculate how many years after that first data set. Now in our calculator, we'll hit Stat, Edit, and we're ready to start entering our data. So the years will go into L1, School A put into L2, School B put into L3. Once you have all your data in, your tables should look like this. Again, if it seems like I'm going too fast, just go ahead and pause it. This is not live TV. Once our data is in, we'll go second, quit, and hit stat again. Now we are going to calculate. So we're going to calculate first the years with school A. So we'll go to calculate. We're in linear. So we're going on number 4. And our L1, remember, is your years. L2 is school A. Perfect. We are going to store this one so that we can calculate when they are the same into our y equals. So we're going to hit alpha, trace. We'll store this into the y1, and we'll calculate. So there's your equation. If you want to write that down and type it in by hand, you can. But if you do the store equation into y1, it is now in your y equals. From here, we'll hit stat again. We'll go over to calculate, down to number 4. Now this time we're calculating school B, so I'm going to be using a different list. So if I do this same list again, I'm still calculating school A's enrollment. Here's how you change a list. Your lists are these blue icons on the numbers below. You need to use second to get to those. So we're going to use list 3. I'm going to hit second and then the number 3. That's going to change that to list 3. Now we go to store, alpha, trace. I've already stored something into y1, so I'm going to go down 1. I'm going to store it into y2. Then I can go to calculate, and there's our second equation. Now you go into y equals. Your first equation, you got the slope of -3. That was predictable. Our school A is going down. School B, we've got that slope of 14. Now, if you go to graph, you'll see some of it, but where is our other school? Well, remember our graph is at 400 or 0 to 400, so our y-intercept of this was in the 600s, y-intercept of this is in the 400s, so we are unable to see it. So we are again going to adjust our window. My X window was looking pretty good. I could see a lot of solutions on that blue line. But my y, because my y-intercepts are so big, was not big enough. So I'm going to go up to 800 on my y and see what happens. So we know we have a y-intercept in the 600s, another y-intercept above 400. And then as these solutions start to produce, we might go even higher on our y-axis. So we're going to make our y window 800. Then we'll hit graph. Let's see what happens. There we have our intersection. The intersection happens pretty quick on the x-axis, so we may want to shorten this down. Maybe we make our window x max of 200 and just see what that does. So not 200. So there's our blue school, there's our red school. Now we're a little bit more zoomed in, we can start finding that intersection. So another review on how to find that intersection, we're going to hit second, calc. Then we'll go down to number 5, intersect. Hit enter, enter, enter. And there's your intersection. So after about 11 years, both schools will be at about 589. And we're not getting direct integers. That's fine. We'll just estimate. So about 11 years, we're at 589 students. So two ways you could write your solution. 11, you'd be at 589, or you could use the year 2016. You're going to be at 589 students. So that is how we can create two lines of best fit and then adjust our window to get back to find where that intersection is and then calculate that intersection. Lastly, we'll talk about some special cases that happen with systems. Systems either have a solution or they don't. So a consistent system means it has a solution, at least one, and we'll talk about when it has more than one. Inconsistent means it has no solution. And we've already kind of seen the systems that have solutions. We see some type of contact between the lines. So you might want to think about what is inconsistent going to look like if the two lines never touch. What would that look like? Independent is a type of consistent system, means it has one solution, and then dependent is another type of consistent system, means it has infinite solutions. So both independent and dependent would be considered consistent, and then we can break it down further, talking about whether they're independent or dependent. So from above, where we talked about the definitions, there's 3 different scenarios that can happen. First, you have intersecting lines. So this first intersecting lines, this would be considered an independent system. You could have what are called coinciding lines, which means they're always going to be in contact, which means they have infinite solutions, dependent system, or we can have an inconsistent system. So those are the 3 scenarios that can happen when you're dealing with linear systems. The main aspect of intersecting lines is that your m, your slope, is going to be different. If two lines have a different slope, they will eventually intersect each other at one single point. The key characteristic with coinciding lines is that the slope will be the same and the y-intercept has to be the same. So they have to be basically the exact same equation to be a coinciding line. And when we have the same slope, same y-intercept, that would be a dependent system. And lastly, to have parallel lines, which will produce a inconsistent system, is when the slope is the same, but the y-intercept is different. So the lines are starting at different positions on the y-axis, but with their slopes being the same, they can never catch up to each other. They will never intersect. They will be parallel. So there are the 3 scenarios. If your slopes are different, you're going to have an independent system. If your slopes and y-intercepts are the same, you'll have a dependent system. If your slope is the same but your y-intercept is different, you will be dealing with an inconsistent system. And the main theme in all 3 of these is the slope and y-intercept. So we are going to put our equations into y equals mx plus b slope-intercept form. So we'll take each equation, put it into slope-intercept form, and we'll notice that the blue equation that we're dealing with has a slope of 3/4. And the red equation has a slope of 3/4. So they do have the exact same slope. And we look at the y-intercepts. The y-intercept of this is 3/8. The y-intercept over here is -3/2. So they have different y-intercepts. That'll bring us to these parallel lines. So this type of system would be inconsistent. And there you have it. So today's learning target, we looked at having a couple different ways to solve these systems, and then we finished up with classifying systems. Thanks for joining.